Hi everyone, welcome back to my channel once again. I hope all of you are doing so great. Today we are going to discuss about the other atomic models like which is given by Rutherford and Neil Bohr model of an atom. So please do watch the complete video to gain the complete knowledge. Alright, so let's start today's session without any further delay. In the previous class, we discussed about Dalton's atomic theory and J.J. Thomson's plum pudding model and the CRT experiment. So you can go and check out that video also before watching this video. Okay, so let's start today's session. First is the Ernest Rutherford model of an atom. Actually, this is the like third model of an atom. Not first, because first we did the Daltons, and next the second was the J.J. Thomson's. Okay, so Rutherford he discovered the proton. When he discovered the proton? In the year 1917, he discovered the proton and he did his famous gold foil experiment. Okay, so what was the famous gold foil experiment was? Let's see this. So basically, gold is highly malleable metal, right? You know that. Highly malleable. Malleability is also high and ductility is also high. So malleability means we can convert a gold into a very thin sheet, right? Like you may have used the aluminum sheet which are required for like food wrapping. So aluminium is like beaten up and converted into a very thin sheet. Similarly, gold also we can convert it into a very thin sheet, like more thinner than the aluminium as well. How much thin it is? That much thin, like it is the thickness. If I talk about the thickness or thinness, is the thickness is like the size of one atom. That much thin. Okay. So, like in a sheet of gold, the thickness is just one atom size. All right. So, this is the reason that Rutherford chose gold for his experiment because it's a highly malleable metal. Clear? So, now what he did actually, he chose gold and in this chamber, he put some like helium, radioactive helium metal. All right. Now, through the radioactive helium metal it was eliminating of course the radiation, the alpha radiation particles was moving out of this and it was going towards this, like he was basically bombarding the alpha particle to the gold foil. Okay, now, when he bombard the gold particle, there is the detector. This you can see there are so many detectors were attached over here, connected, where the gold was, the atoms were going, all right, and then it's getting reflected, and detector was basically detecting the particles. Okay, so most alpha particles are traveling through the foil, which was undeflected. Let's say this first of all. In his experiment, like according to the J.J. Thomson, atom was like a watermelon model and electrons are embedded into it, right? And according to J.J. Thomson, all the like what J.J. Thomson, because Rutherford was doing his experiment based on the theory which was provided by J.J. Thomson's only, right? So, according to that, he expected that all the uh, positive charge like the alpha particles which were having +2 charge will be passed through, like without any deflection it will pass. Okay, this was the expectation. Okay, there is something called as expectation versus reality, right? So this was the expectation of Rutherford, but what actually he got, he got that most of the particles, alpha particles, were passing only without undeflection. But there are some alpha particles which get deflected over here, and there are very few alpha particle which bounce back. He didn't expected that. Like how the alpha particles are bouncing back. He didn't expected that, no. So that was the thing, like which trigger his mind. Oh, there must be something in the center of the atom like which is causing the bounce back of these alpha particles. So what is that something? So basically we know that alpha particles are the positive 2 plus charge. And we also know that positive charge are repulsive, right? Same charge are repulsive in nature and the opposite charge are attractive in nature. So if someone is bouncing back, something is bouncing back from the this part, this side portion, the center portion of the atom, so there must be some positive charge particles. That's why they are bouncing back. Don't you think so? Rutherford also thought the same thing. Okay. So what was the observation basically? He said that most of the all the alpha particles, they went through the gold foil and there was no deflection. This shows that most of the atoms are having empty space. Okay, as there are no deflection. All right. Now, several several particles pass through the gold foil and there were some deflections were there. So he concluded that the nucleus must be a positive charge. There should be something positive charge present at the center of the atom, which is causing the repulsion of the alpha particles. Okay. And next he said that only few particles, how much few? Like 1 out of 12,000 particles, that much few. 1 out of 12,000 particles were bounced back 180 degree. So this shows that the nucleus, the center, he named the center as a nucleus. Okay, the center of the atom is very small. It's so small, and that is containing the positive charge as well. Okay, so this was the gold foiled experiment done by Rutherford. So what conclusion he after this gold foil experiment, he proposed his own atomic model. He said that how the atom would look like, and it is completely different from J.J. Thomson's atomic model. Okay, so he said that positive charge is only present at the center. Okay, it is called as the nucleus and it is very small as compared to the size of the atom. Nucleus is very small because as compared to the size of the atom is very big. Okay, electrons are revolving around the nucleus in some orbits. Okay, and most of the space in the atom is a empty space. All right, like you can see, these space are the empty only. Electrons are here in this orbit. Okay, it's very similar to our solar system. So this is also called as the planetary model of an atom. Like in between, in at the center of the solar system, we have the sun. Okay, and the planets are revolving around the sun, and in between the planets and the sun, whatever the space is, it's empty. Yeah, there are some asteroids like they're in the solar system, but just forget about the asteroids. Other than the asteroids, it's empty space only, right? So similarly in the atom also, nucleus is present at the center, which is containing protons, the positive charge. Electrons are like planets which are revolving around the nucleus, and in between all of the space are empty space. Clear? This was said by Rutherford. Alright. Now I'm going to show you a video which is going to explain you in a better way about the Rutherford's experiment. Please watch this.
Rutherford's model of an atom. A number of scientists worked on the structure of an atom. One of the first scientists was Sir J.J. Thomson, but his model could not explain the results of several experiments. One of those experiments which could not justify the Thomson model was done by Rutherford. Rutherford's experiment got popular by the name of alpha particle scattering experiment. To understand about his experiment, let us first see what alpha particles are. Alpha particles are emitted by radioactive substances. These are helium ions with double positive charge. Now let us look into the details of the alpha particle scattering experiment. The setup of the experiment consisted of a thick lead box with a hole on one of its walls, a slit, a thin gold foil, and a rotating detector at the end. Inside the lead box, a radioactive substance rich in alpha particles was kept. Now, Let us see the experiment. Alpha particles emitted from the radioactive source passed through the hole and entered into the slit to get streamlined. The thin streams of the particles then bombarded the gold foil and got scattered in different directions. Their scattering pattern was shown by the detector. It was expected from the Thomson model that it should show a large number of deflections. But something else was observed actually. The detector showed that most of the alpha particles passed through the gold foil as such without showing any deflection. Only a few of them showed deflection in different directions. A very few of them, essentially 1 in 12,000, rebounded back. Such observations led to significant conclusions. Let us see what those were. As most of the particles passed undeflected, Rutherford concluded that most of the space inside a gold atom was empty. A few particles were deflected from their path by small angles, indicating that there must be a positively charged center, which was repelling alpha particles. As these particles were few in number, this led to the conclusion that a positively charged center occupies a tiny space. The few particles that are rebounded back indicate that all the positive charge of the atom was concentrated in a very small volume in the center. Rutherford named this positive center of the atom as a nucleus. Looking at the proportion of the particles undeflected, deflected, and rebounded, and based upon some calculations, Rutherford concluded that most of the mass of an atom is concentrated in its nucleus. Based on all these conclusions, Rutherford suggested an atomic model, which was known as the nuclear model of atom. According to Rutherford's nuclear model, there is a positively charged center in an atom called nucleus, and all the mass of the atom is due to this nucleus. It also suggested that electrons of the atom revolve around its nucleus. This model was also known as planetary model, as the nucleus of the atom can be compared to a miniature sun, and electrons revolving around the nucleus can be compared to the planets revolving around the sun. But this model did not get much acceptance, as it said that the electron keeps revolving around the nucleus. However, later it was found that any charged body while moving in a circular motion undergoes acceleration. On undergoing acceleration, it should use some energy. So the energy of the electrons should keep decreasing. As a result, the path in which the electron is moving should keep becoming smaller, and thus, finally, it should fall into the nucleus, and hence the atom should collapse. So, the nuclear model could not explain the stability of the atom, and this was its major drawback. Let's recap. Rutherford gave a nuclear model of an atom which was based on his alpha particle scattering experiment. According to the Rutherford's model of an atom, all the positive charge and mass of an atom is concentrated at the center. The center of an atom is called the nucleus. The size of the nucleus is very small as compared to the size of the atom. The electrons of an atom revolve around the nucleus. The major drawback of this model was that it could not explain the stability of the atom.
Alright, I hope the video was sufficient for the better explanation. Now, according to this model of the atom, like what is another observation? Like, is there something which is not relevant, irrelevant, or like drawback? So see, like have you ever played with the marble? Like takes you can play right now also if you haven't played. Take a marble, like marble, the kanchas. Okay, kancha. So take one marble in a pan, okay, and just rotate the pan in a circular way, like this. Slightly rotate the pan in a circular manner, like this. Okay, what will happen? The marble will move in the outermost circumference of the pan. Correct? Now stop rotating the pan. Okay, make your hand stable. What will happen? The marble which was rotating at the circumference of the pan, it is now like the speed of the marble is decreasing and it is now coming towards the center of the pan, right? That happens. You can play this game as well. So similarly, if Rutherford said that electrons are revolving around the nucleus, so of course electrons are having some energy, it requires some energy to revolve around the nucleus. Okay, so when it requires some energy, that means it is using the energy, it is radiating the energy to revolve around the nucleus. Correct? So as it is radiating the energy, it should also, lose energy and come closer to the nucleus, and it should have fallen down in the nucleus only. Like I just gave you the example of a marble. You stop moving your, rotating your pan. What will happen? The marble will come towards the center. Okay, automatically it will come. Why? Because while you were rotating your the pan, you were providing the mechanical energy. Okay, now it's you have stopped rotating, so it's not getting any energy, so it will automatically lose energy and come towards the center of the pan. Similarly, it should have done for the electrons also, like it would have lose energy and finally fall into the nucleus. And you know that if electrons are falling into the nucleus, so atom is going to be very unstable, right? And if the atoms are unstable, so no matter would have exist in the nature. Okay? So, but this does not happen. There are so many different types of matters which are existing in the nature. We know that. So Rutherford could not explain this, how this is happening. Okay, due to this atom should be highly unstable, hence matter would not exist in the form that we know. But we know that atoms are quite stable. Atoms are stable. That's why the matter exists, right? Otherwise, what would happen? No matter would have exist. All right. So Rutherford could not explain this. Now, who is going to explain this now? So another scientist called Neil Bohr come into this scenario. Okay. Neil Bohr's models of an atom. Let's discuss this. So Neil Bohr said that electrons are moving in an orbit, but it is not coming down towards the nucleus like that. When the electrons are moving in an orbit, they are having their own special orbit, and those are called as the discrete orbits. So the electrons are moving in their discrete orbits, and these discrete orbits are having their own specific energy levels. So these orbits are also called as energy levels or energy shells, whatever you say. Okay, orbits or shells, everything is correct. And while the electrons are moving in these energy shells, they do not radiate energy. Okay, like how? Let me explain you this. So have you ever seen like the runners? They move around in a like circular path, circular ground basically. Like for the racing purpose. Like this is the circle I'm making. There is the circular 1, 2, and 3. Like suppose there are three runners are there and they are racing. Okay, have you ever seen like in the Olympics games and other games also you can see this. They always move, like circular path. In the circumference of the ground they are running, racing. Suppose these are all the runners are there. Now, the runner which is uh, like moving in this path, just suppose forget about the Olympic, just say that runner, the first, second, and third. Third runner, which is like first runner, which is moving in this circle. This is a kind of smaller circle. It would He would take like less time to complete this circle, right? And he would require less amount of energy. Suppose he is completing this circle in 5 minutes. Okay. Now, if the second runner is supposed to complete this circle in 5 minutes, he has to cover a long path. Correct? So he require more energy. And similarly for the third runner, if he wants to complete this circle in 5 minutes only in the same time period, he will require more energy because this circle, the outer circle is having, more longer path. Correct? So similarly, when the electrons are rotating in their orbits, they are having their own energy level. Okay, and in the lesser the orbit, Okay, the first orbit is going to have minimum energy level and the outermost orbit is going to have the maximum energy level. And when they are revolving around the same orbit, like in that particular orbit only, so they are not radiating any energy. They are not losing any energy or gaining any energy because this orbit requires a particular fixed energy level. Okay, but now if the electrons, like if these runner, like suppose this third runner is changing his lane and he is moving in the second lane, okay, what will happen? Now he will require less amount of energy, right? He won't require that much amount of energy because the path is like more shorter as compared to the outermost circle. So when an electron is moving from outside to inside orbit, it is like losing its energy because now it requires less amount of energy. So it lose the extra energy what electron had. But just imagine another scenario. This first runner is moving towards the outermost circle. Now, because he is moving towards the outermost circle, now of course he will require more energy, right? Similarly, when the electron is moving towards the outermost orbit, like changing the orbit, okay, like one orbit to second orbit, it could be any orbit, okay? So it gains the energy, okay? I hope this is clear to all of you. So electrons emit or absorb energy when it jump from one orbit to another energy level, okay? When it jumps from higher energy level to lower energy level, it is losing the energy, emitting the energy, while it absorbs energy when it is jumping from lower to higher energy level. Okay, I hope this point is clear to all of you. So this was the Niels Bohr's model of an atom. He also named the energy levels. What was the name? KLMN or 1, 2, 3, 4. Clear? Alright, so let's do watch a video for a better explanation.
Bohr's model of an atom. Prior to Bohr, there were a number of scientists who were working on the structure of atom. Rutherford was one of them, and his model was the closest model to the Bohr model of atom. In fact, Niels Bohr had helped to overcome the problem in the Rutherford's model of an atom. The Rutherford's model of an atom had a major drawback, that it could not explain the stability. It showed that electrons in an atom revolve around a positively charged center called nucleus. However, later on, it was found that any particle in a circular motion would undergo acceleration and thus would lose energy. So, the electron would take a spiral path and would finally fall into the nucleus and the atom would collapse. But this does not take place in reality. Bohr said that electrons do revolve around the nucleus, but their energy remains fixed. He explained that the energy of electrons remains fixed because they are restricted to some fixed orbits. Each of these orbits is at a fixed distance from the nucleus and is associated with a fixed amount of energy. These orbits with fixed energy are known as discrete orbits or energy levels. These energy levels are represented by the letters K, L, M, N or the numbers 1, 2, 3, 4 starting from the center. So, the final model of Niels Bohr was similar to the Rutherford's model of an atom, which states that an atom consists of a positively charged center around which the electrons revolve. The only difference was that in the Bohr model, electrons revolve around a nucleus in fixed orbits with fixed energy. For his work on structure of atom, he got a Nobel Prize in 1922. Let's recap. Bohr model of atom suggested that an atom consists of a positively charged nucleus and electrons revolve around it in special orbits called discrete orbits or energy levels. The energy of these discrete orbits remains fixed. These energy levels are represented by 1, 2, 3, 4 or KLMN starting from the center. Bohr got the Nobel Prize for his work in 1922.
Alright, so that was about the Neil Bohr's atomic model. Now, there is another thing which is called as Bohr and Bury scheme. Okay, Bohr and Bury, they were two scientists and they said that like how much electrons is going to present in one orbit. They find out that. Okay, for that they give a very like easy formula, that's 2n square. Okay, n is representing the orbit number. Like the first orbit is like 1, so n is equals to 1. For the second orbit, n will be is equals to 2. For the third orbit, n will be is equals to 3. Okay, 2 to the power n square. All right, and you know that the name of the orbit is like KLMNO. Okay, so if we put all of this in this formula only, now we get to know that in the first orbit, which is the K orbit or K shell, number of electrons are 2. In the L shell, number of electrons are 8. In the M shell, number of electrons are 18. In the N, it's 32. In the O, it's 50. Okay, so that's the that's how we do the electronic configuration as well. Okay, electron distribution is also done according to that. Okay, so this is the basically Bohr and Bury scheme. All right, now here comes another thing. Like while doing the electronic configuration, a question might have arisen in your like head or in your mind that we are doing a 2 8 8 and then we are just doing like 2. Why not in the third shell if we can put 18 electrons according to the 2n square formula? Why we are not doing 10 over here? Right, we should do this 10, right? But why we are not doing so? We are not doing this because when I'm talking about the subshells, like shells, when I'm talking about the shells, suppose this is the nucleus. Okay, and let me draw the orbits surrounding the nucleus. So orbits, when I'm drawing the orbit, it's not a single line, it's not that much thin. It's basically like this. Okay, it's like this. Now in this orbit also, if I show you in very zoom manner, there are some subshells are there like this. Okay, these are the orbit. Light blue color is representing the orbit and this dark blue color is representing the sub orbits or subshells, which you can say. Okay, so what are the name of the subshells now? These are S, P, D, F. Okay, so in the first orbit, there is only first one subshell is present. In the second orbit, two subshells are present. In the third orbit, three subshells are present. In the fourth orbit, four subshells are present, and like that. Okay, so these are the subshells. All right. So now, like fourth, let's write the fourth orbit also. 4D, 4F. Now, according to this, subshells are having their energy levels. Like I mentioned it about the orbits, the shells are having the energy levels. So similarly, inside the shells, there are the subshells which are also having their own energy levels. Okay, so like first subshell is filled first of all, then the second 2s subshell is getting filled. Okay, 2p, after 2p, the third subshell is getting filled in the third orbit. In the third orbit, first subshell is the s, second subshell is the p, and third subshell is the d. But after this 3s, 3p is going to get filled up, but after 3p, 3d is not going to get filled up, 4s is going to get filled. Okay, like this. So this is the reason that in the basically the first subshell, the S subshell can hold on up to 2 electrons. The P subshell can hold on up to 6 electrons. D subshell can hold on up to 10 electrons. Okay, so whenever in your junior grades you are just doing till 20 elements, right? So like 2 plus 8, that is 10, and here this is basically 20 electrons are there. This is the calcium. Okay, all right. So here you can see after the 8 electrons get filled, like in the third subshell, 2 for 3s and 3p, 6. 6 are getting filled up. Now this becomes 8 na? In total it becomes 8. So what shell is going to now get filled on? The fourth cell. So 2 comes to this. So K, L, M, N. In the N shell, 2 electrons are going to filled up. Okay, this is the explanation. So this is the reason that in the M shell we are not writing up to 18. All right, after writing 8 we move on to the next shell. Okay, in the N. So this is the reason. Otherwise, according to the Bohr's theory, there will be 18 electron will be filled up, and which is correct because you see, like later on, let me just elaborate this because these are total 8. S and P is totaling 8, and D there will be 10 number of electrons, right? So after this 4s2, there will be 3d. So total comes 18 only, right? And these will be the like next elements after 20 elements when you are going to study this in higher grades. After 20, you will be studying these things. Okay. Now in your ninth grade, there is up to 20 elements only. So you are just studying about KLMN. I hope this is clear to all of you. Okay. All right, so this was the Bohr's and Bury scheme and how we fill the electrons in the subshells. And from this only we write down the electronic configuration. And how we write it down like this. So here you can see like all of the different elements are having different number of protons. So different number of protons are saying the atomic number. Okay, and according to the atomic number, of course, the number of electrons and number of protons are same in a stable atom, right? So like for hydrogen it is 1. So in the K shell it is 1 electron. For helium it is 2 electron in the K shell, like this. In the lithium it is 2 and 1. L shell is also getting filled. All right. In the beryllium you can see electrons are now getting filled in the L shell. Here you can see up to neon, L shell is complete now. Okay, so neon is having valency 0. After this, now M shell is going to get filled, and like here till argon is written. Like if we go like above argon also, like in the chlorine, we just write, for chlorine it's like, sorry, for calcium, not chlorine. Chlorine is 17. It's like 2882. Okay, 20 atomic number. For potassium, it's 19. So it's going to be 2881. All right. So I hope the Rutherford's model and the Neil Bohr's atomic models are clear to all of you. That is it for today's session, students. If you like this, if you are understanding my teaching, please share this with your other friends also as well. Okay, and hit the subscribe button. Okay, so that's all for today's session. Other topics are going to cover in the next video. So please wait for the next video. I post videos every Tuesday, Thursday, and Saturday. Okay, so do watch the next video as well. Okay, take care. Have a nice day. Bye bye.